because unimolecular substitution and unimolecular elimination always accompany one another, we need to address the question, when is the substitution pathway going to be predominant, and when is the elimination pathway going to be predominant? In general, substitution is predominant for good Lewis spaces that are weak Bronsted-Lowry cases. So what makes something a good Lewis space but a poor Bronsted-Lowry case? And to think about that, we need to introduce another way of looking at acidity and basicity. In U acid-base theory, referred to as hard and soft acids and bases. We consider an acid or a base to be hard if they have localized charge on a small atom. So we have all of our negative charge on one atom, and that atom is quite small, which means we can't stabilize that by polarizability. So examples of hard bases are things where you have a second row element like fluoride, or hydroxide, or any of the alkoxide ions. Epoxide ion shown here. Things like arid ion, where the charge is on nitrogen, right? And substituted amines, a very hard base that's fairly common, which in addition to being hard is also sterically hindered, is diisopropylamide. And of course, carbon anions, like CH3- would be a very hard base. All of these are negative charges that are localized on a single atom and are not able to be stabilized by hyperconjugation. So in most of these cases, you also see that the conjugate acid is a very weak acid, pKa of 50 for methyl, pKa in the 35 range for these ammonias, in the 15 range for those. HF is a reasonable acid because fluoride is so electronegative, but fluoride is also still a hard base. Hard acids are also small and localized charge. So when you think about a hard acid, you would think about a proton, right? That's about as small as you can get. So hydrogen is a hard acid, but also small ions like lithium ion is a relatively hard acid, right? Because that's the second row cation, and highly charged ions like aluminum 3+, because you have 3 positive charges on aluminum, and although aluminum is in the third row, it's not, once you have these 3 positive charges on it, you're back into a neon configuration. So small localized charge, by contrast, are polarizable. So something like iodide ion, where the charge is localized on a single atom, but it's highly polarizable, so it can stabilize at negative charge, or residue stabilized. So when you see something like acetate ion, the charge is on a small atom, oxygen, but it's not really a full negative charge because you have a resonance much localized charge on a small atom. And soft acids the same way. Soft acids have delocalized charge. And what's most relevant to us, especially tertiary carbocations, because then that charge is spread out onto the adjacent sigma bonds by hyperconjugation. So what we're looking at when we're looking at substitution versus elimination is elimination is the base reacting with the hard acid, the hydrogen on the beta position. Substitution is the anion. And if we have a soft acid, a soft base is going to prefer to react with it. So iodide will do substitution instead of elimination because the soft bases like to react with soft acids, whereas the hard bases like to react with hard acids. So if we have a soft base, probably we're going to get substitution as our major pathway. If we had a hard base, we're probably going to get elimination. Make sense? Hard bases prefer hard acids, soft bases prefer soft acids. Numerous other acid-base theories. If you were to take advanced inorganic chemistry, you would learn what can be an acid and what can be a base. So let's consider the reaction of a secondary alkyl halide with a good leaving group. This time we'll use triflate. Trifluoromethane sulfonate. And we're going to carry this reaction out in a protic solvent, ethanol, which is going to enhance the unimolecular pathway and give us a mixture of SN1 and E1. And we're going to do this reaction with sodium fluoride as our nucleophile. So we're working with F-. First step will be the loss of the leaving group. That will be at equilibrium. To get a carbocation intermediate, the secondary carbocation. And then fluoride ion will have a choice of attacking one of these beta hydrogens on either the methyl group or on the propyl group, or reacting with the carbocation intermediate. If we react with the carbocation intermediate, we would expect to get SN1 substitution, and we would expect to get a racemic mixture. So we'll show that squiggly line showing that this is racemic. Fluoride is just as likely to come from the top face as it is from the bottom face. And if alternatively fluoride ion attacks one of the hydrogens, we can get an E1 pathway. We actually have three potential E1 products that we could make, because if it attacks this hydrogen, it could generate either the cis or the trans stereochemistry of that pi bond, right? Either cis2 pentene or trans2 pentene. So there are five possible products if you count the two different enantiomers of the 2-fluoropentane. And we have to determine which of these products is likely to be the dominant product. We know that it's likely to be unimolecular because we're in a secondary substrate with an excellent leaving group, and we have a protic solvent, and the protic solvent is going to stabilize that carbocation and increase the rate of the SN1 reaction. And we also know that we have a hard base. The hard base is probably going to like to take off the hard acid, the hydrogen. So we might expect that the E1 elimination pathway would dominate in this case over the SN1 pathway. There's some steric hindrance for the SN1 pathway. Even in the second step, it's planar, so there's not as much steric hindrance as there would be for the SN2 pathway. And those hydrogens are readily accessible, and fluoride is a hard base. Within the E1 pathway, we know that the more stable the transition state, the faster the reaction. So the secondary, the di-substituted pi bond should be favorable over the mono-substituted. And we expect to see only traces of 1-pentene, if at all. Trans-2-pentene is more stable than cis-2-pentene because we avoid this steric hindrance here, these two groups being on the same side of the ring. So we expect trans-2-pentene to be the major product and the cis-2-pentene to be the minor product within the alkene series, right? Mostly very little of the even less stable primary or mono-substituted alkene. And we might expect that E1 will be a larger pathway in this case as opposed to the SN1 because of the hard base. By contrast, if we were to take that same substrate, the triflate, formed from 2-pentanol, and instead of reacting it fluoride, we were to react it with sodium acetate, which is a resonance stabilized and therefore softer base. The mechanism will be the same in the first step. Generate secondary carbocation. Eliminate triflate ion, but now we might expect the most favorable pathway with a softer base to be the substitution pathway, SN1. Again, generating a racemic mixture of acetates. But this time it's a major product where the E1 elimination will be less favorable. Still, carbon by mistake. Still, we would expect the trans product, the same set product, to be the dominant alkene. Now we would expect that to be the minor product from the softer base. And if we were to switch to an even softer base and use sodium iodide, we would expect to get almost exclusively SN1 and very little E1 competition. Increasing the concentration of sodium acetate or switching the solvent to DMSO. So if we were to use 5 equivalents of sodium acetate and we were to run that solvent in DMSO, we would actually expect to get primarily a stereospecific reaction with inversion of configuration by an SN2 pathway. 5 equivalents of sodium acetate is going to increase the SN2 reaction rate, because the SN2 reaction rate depends on the concentration of the acetate ion. But the SN1 reaction rate does not depend on the concentration of the acetate ion. The concentration of the substrate. So by increasing the concentration of the nucleophile, we're going to increase the SN2 reaction rate without affecting the SN1 reaction rate, which is going to cause SN2 to predominate, and we're going to increase it by lowering the activation energy through solvating that carbocation and leaving the anion naked, so it's more likely to react. So we can get an SN2 reaction, an SN1 reaction, or an E1 reaction on this secondary substrate by changing the conditions, changing the base, so it's a harder or a softer base, changing the solvent to try to enhance an SN2 versus an SN1, or changing the concentration of the nucleophile to again try to enhance the SN2 reaction rate. If we use a hard base like hydroxide and increase the concentration to 5 or 10 equivalents, we'll actually get the fourth possible pathway to dominate.